Hi, my name is Tiago. I am a PhD student at the TUM, at the mathematics department. And here I'm working here with Dr. Rita as a tutor for this class.
Okay, so welcome everyone to today's central exercise class. You've just heard Tiago's introduction. Tiago will be monitoring the chat channel today. So as usual, if you have any questions, please just ask in the chat. Let me try to see if I can share my screen with you so you actually can see what I write. Yeah, just a second. So that should be working, hopefully. Okay, you should now see my iPad screen. If you don't, then please just post a message to the chat channel. As usual, we have a live chat during this webinar. It's available on chat.tum.de. Please use the channel MA9714 for central exercises. Okay, Tiago will be monitoring that channel, and whenever a question comes up, I'll try to answer it here on the air. Okay, so let's start with today's webinar. We'll be discussing sheet number 2 today. And before we start, I'd like to take a quick poll and see what you found particularly complicated or not so complicated for today's session. Just let me find that. Okay, need to take a quick break for the screen sharing to do that actually. So let me just start that poll. There is not a reference to the problem numbers specifically, but more to problem types. So I'd like to know whether you had any difficulties in working with complex numbers or with eigenvalues, eigenvectors specifically, so that maybe we can do another problem on this type this time or next time. Okay, I'll give you a few more seconds to cast your vote. And then I'll close the poll in 5 seconds. Okay, so let me see if I can show you the results here. So there's a pretty huge majority for solving differential equation systems through the organization of a matrix. So I'll probably have to prepare something for that. So probably we'll talk a little more about this next week. Okay, I'll make a note. Good. Thanks a lot. So let's get back to the screen sharing. Yeah, I hope you're getting my iPad screen. And let's have a look at today's central exercise problems on sheet number 2. So first problem we're going to talk about is exercise C28. That's a problem on complex numbers. And the task here is to determine the real and imaginary part of a given complex number. That number is Z 1 plus I over 1 minus I to the K. And K is a positive integer. So basically what we want is a representation of Z in the form some real number plus another real number times I. So we want to separate the real part. This is this alpha here, and the imaginary part, the beta of our complex number. And with fractions, there is an easy way to do that. A neat little trick that you need to know. So let me write this down once more. What you do is basically you expand the fraction in a way that makes the imaginary part in the denominator go away. And for that, we just use a binomial formula. So in this case, what we have here is 1 minus I. And we'd like to use the formula a minus b times a plus b is a squared minus b squared. Because if we can square this I part, then we get an I squared, and I squared is minus 1, so the I just goes away. Okay, so what we have to do is we have to expand the fraction with 1 plus I to make that happen. So same thing here. And if we do that, what we get is for the numerator, where that is 1 plus I squared. So we get 1 plus 2I plus I squared divided by 1 minus I squared to the k. Okay, now I squared is minus 1. So this is a minus 1. And this is a minus 1. So in the numerator, we get 1 plus 2I minus 1. That's just 2I. And in the denominator, we get 1 minus minus 1. So 1 plus 1, that's 2. Okay, so what we have is actually I to the k. And let's simplify that a little more. Basically, there's 4 different cases that can happen here for I to the k. If we have k equal to 0 or 4 or 8 or whatever else is a multiple of 4, then I to the k is simply 1. Yeah, so for I equals 0, you just know about that. For the others, I'll hope to convince you in a few minutes or seconds. If k is 1, then we get I. If k is 2, then we get minus 1. Oh, sorry, it's not I, of course. My bad. That's a k here. And finally, if k is 3, we get I squared times I, so minus I. And now if k is 4, we have minus I times I, that's minus I squared, or plus 1. So we're back at this 1 thing here. Yeah, so for 4, that same thing happens as for 0. For k equals 5, it's 1 times I again. For k equals 6, it's minus 1. For k equals 7, it's minus I, and so on. That whole thing repeats in that cycle. So we get 8 for this case. We get 9 here, we get 10 here, and so on. Okay, so those are the 4 possible outcomes of that equation, depending on the value of k. Okay, hopefully in an easy start to the central exercise session. Let's see if there are any questions already. Tiago.
There was only one question. Yeah, they said, why is I squared equals to minus 1? But they said it's the definition, or maybe you have a better answer.
No, I don't really have a better answer. Yeah, so the question is, why is I squared minus 1? That's basically the definition of I, right? You remember that we introduced I as the complex number consisting of those 2 parts here. You do remember we introduced a complex number as basically a vector that has 2 components. I corresponds to the vector 0, 1. And then we just we defined a multiplication on that set of tuples of real numbers that looked a little strange. And if you just apply that definition to this I here, then you get the result minus 1, sorry. Yeah, so that's basically what defines the complex numbers if you want. Anything
Okay,
else?
so yeah, there are many questions now. So would it be correct if I wrote z is equal to e to the power of I pi k over 2?
Okay,
and
let me
then
write this
as
down. What did that say? C equals?
to the exponential of I pi k over 2?
Like this?
Yeah, and then as cosine of k pi over 2 plus I sine of k pi over 2.
Cosine of pi k over 2 plus I sine?
K pi
Like
over
this?
2. Yeah, exactly.
Okay, so you're referring to Euler's formula, I presume. So that's basically a straightforward application of Euler's formula, and that is of course correct. Yes. So you do remember, hopefully, that we've talked about expressions of the form e to the ix with a real x, and Euler's formula says, well, that is cosine of x plus I sine of x. So that's just an application of that formula with this expression here being x. Correct?
Yeah. Okay, so the next question is, if a matrix is not diagonalizable, does this automatically mean that it doesn't possess an eigenvector basis?
Can we talk about these questions a little later when we get to the eigenvalues, eigenvectors? Anything about complex numbers at this point?
Yes. What would be the real and the imaginary part in the answer of 2.8?
With the real and the imaginary part, okay, if you want to have a look at the real and imaginary part in this answer here, so this is the answer we're referring to, then again, we have to make a case distinction. So obviously, for k equals 0 or 4 or 8 and so on, what we have is the real part is 1, while the imaginary part is 0. In this second case here, the real part is 0, while the imaginary part is 1. Yeah, basically it's 0 plus 1 times I. Here we get a real part of -1 and an imaginary part of 0. And in the last case, we get, again, a real part of 0, an imaginary part of -1 in this case. So the number 0 plus -1 times I. Okay, I hope that answers the question.
Okay. And the last one that I didn't quite understand, doesn't over 0 is also a special case? Why does this special case applies for over 4 and over 8?
Oh, so the question is 0 a special case? And why does this also apply to 4 and 8?
Yeah.
Well, it's not so special after all. So if you have a look at what we do with 3 here, so you remember that set to the third is -I, then what happens if I multiply this with set once more? And you remember that set is actually just I to the k, yeah? Now let's make this a little more clear. Let's say we define a complex number w, that's just I, okay? Then w to the third, we agreed on that already, is -I. And now if we want to compute w to the fourth, so that's basically the case k equals 4, then what we have is -I times I, or -I squared, or -1 or +1. Yeah, so for the case k equals 4, we're getting back to +1. And that case 0 is not special after all. Okay, I hope that answers the question. If I didn't understand that correctly, then please just post a follow-up to the chat.
Yeah, okay, that's all.
Okay, then let's move to the next question, and I'll answer that question about eigenvalues and eigenvectors probably after 2:10, because that's precisely about that thing here. Please remind me of that question, Tiago. Okay. So let's move on to C29. So that's a neat little problem of a more theoretical nature. We have given a vector u that is a direction in R to the n. Direction basically means it's not the zero vector, so it actually points in some direction. Okay, and then we consider the projection. So a mapping F from Rn to Rn is the projection onto that direction u. You hopefully remember from the first semester that we defined the projection like this. We just took the scalar product of that vector u in the direction with the input x, and we divided that by the scalar product of u with itself times u. This scalar product of u with itself, that is basically the norm of u squared. Okay, so if you like this representation a little better, what you can also do is you can say this is basically the normed version of u, scalar product with x, and then multiplying this with the normed version of u. Yeah, so with this scalar product, we basically computing the part of x that points in u direction. So the idea of a projection, let's have a very quick sketch of that. Let's say this is our vector u. Okay, then we have a vector x, let's say that points in this direction here. That's our x. And what we do with the projection is basically, we decompose that x into a part that is parallel to u and a part that is perpendicular to u. So that means what we do is we do this projection here like this. So here's a right angle. And then the projection is this part here, parallel to u. So that is our f of x. That's the part parallel to u. And then we have this other part here. That's the part of x that is perpendicular to u. Okay, so that's basically the idea of the projection, to find out the parallel part of any vector to the space that we're projecting on. In this case, the space is defined by just one vector, so it's basically just a line. Okay, and of course we could do that for planes and other subdimensional spaces as well. Now the idea of this problem is to find out about eigenvectors and eigenvalues of that projection. Yeah, projection is a linear mapping. So we can define a matrix that represents it if we have given a basis. And of course, we can then compute eigenvectors and eigenvalues. In this case, we already have given possible eigenvectors, and we just have to confirm that they actually are eigenvectors and determine the corresponding eigenvalue for those. So part A here is we show that u is an eigenvector of f. And of course, we want to know the corresponding eigenvalue for that. So if you look at the graph here and say the input of this projection here is u itself, then what happens? Well, we have this U here. We project U onto U, so we decompose U into a part that is parallel to U and a perpendicular part. Well, what will happen is, of course, the part parallel to U is just U. There is no perpendicular part. So the outcome of the projection of U onto itself should simply be U. And of course, that means this thing adheres to the definition of an eigenvector. Yeah, if we apply the mapping F to U, then the outcome is a multiple of U. In this case, a very special multiple, 1 times U. So the eigenvalue should just be 1. And of course, we can also see this if we just use the formulas. So F of U, just applying that formula. By definition, that is the scalar product of U with itself, divided by the scalar product of U with itself times U. Well, this fraction here, this reduces to 1. So we get 1 times U. And that means 1 is an eigenvalue, and U is an eigenvector of the mapping F. Okay? So U is an eigenvector of F with eigenvalue 1. Okay, so that was part A. Let's see if there are any questions already about this problem. Tiago?
No, there are no questions.
Okay, great. Then I'll continue with part B and see if there are any more questions at the end. Thanks. Good. Part B. The next vector that we examine is a vector V that is orthogonal to U. No, sorry, V. It's orthogonal to U. So we just remember that picture here. We have this vector U, this one here. And now we're looking at a vector V that is orthogonal to U, meaning the setting now looks a little like this here. So that's V. Now, if you project V down to U, what will happen? Well, we have a right angle here. So the part parallel to U, that should simply be this point here. Yeah, there's nothing more to that. And the part orthogonal to U is obviously the whole vector V. So what happens is the projection reduces V to just one single point, and that is the origin. And again, we can have a look at the formulas to find out. So we need to compute the scalar product of U and V divided by the scalar product of U with itself times U. And this scalar product here, U and V, is simply 0 because U, V are orthogonal. And that's the definition of orthogonal. Yeah? Scalar product is 0. So obviously the outcome is 0 times U, and that is the 0 vector. Okay, but more important, the 0 vector is of course the same thing as 0 times any vector. In particular, we can write 0 times V. So that means V also adheres to the definition of an eigenvector, with the eigenvalue being 0 this time. Okay, so what we have is V is an eigenvector for F with eigenvalue 0. And I should maybe add one more remark here. That is, of course, provided V is not the 0 vector. Because by definition, the 0 vector is never an eigenvector. So that needs to be excluded. And luckily it is excluded in the problem statement. I just didn't mention that in the beginning. Okay, so that gives us the second eigenvector and eigenvalue. Any questions at this point?
Yes, there is one question. If we fixed the coordinates for U, how could we compute the projection matrix?
If you fix the coordinates for U, how could we, we compute the projection matrix? Well, same thing as we always do, basically. So let's say we fix some U, and you want the matrix representation of F. Then, of course, you could do this the usual way. You could just say, what we need first is a basis. You need a basis of R to the n because the projection matrix will depend on that basis. Okay? So we do just that. We choose any basis. Well, let's say we agree on a basis that is called B1 to Bn. And then we simply compute the outcomes. We compute f of B1 by just computing that projection. We can do this if we have the coordinates of U and of B. The result will then be a vector in Rn, and we can then represent that result as a linear combination of the B's again. So there are some lambda 1, lambda 2, and so on, such that this can be written in the form lambda 1 B1 plus lambda 2 B2 and so on plus lambda n Bn. So we first compute, first compute that result here. And then we compute the corresponding lambdas. Okay, so these lambdas are the coefficients of the image of the first basis vector with respect to that same basis. And this will give us the first column of our matrix representation. This just consists of these lambdas. So this is column 1 of the matrix representation. And then we just repeat this for the other columns. So repeat the same procedure for B2, B3, and so on. And we get columns 2, 3, and so on. And that will give us the matrix representation. Now, of course, in this case, let me add this, there is a very clever way to determine a basis. So if you have a choice which basis you want, then you can try and be clever about that. There's one possibility for that that is particularly clever. You can just use U as your first basis vector, and then find a basis that is completely orthogonal to U for the rest of the space. Yeah, so we extend that with V1 to Vn minus 1, where V1 is orthogonal to U, V2 is orthogonal to U, and so on. We can't find a basis with these properties, obviously. And if we do that, then what we get is, of course, well, we already know that the projection of U is U itself. So that corresponds to the linear combination 1 times U plus 0 times V1 plus 0 times V2 and so on up to 0 times Vn minus 1. So that first column will be of the form 1 and then lots of zeros. And for the rest, f of V1, we already know that a vector that is orthogonal to U is projected onto the 0 vector. Okay, so that corresponds obviously to this column here. And the same is true for all the other V's, of course. So what happens is the matrix with respect to this choice of basis, with respect to u, v1, and so on, vn minus 1, is then first column is 1, and then zeros, and all the other columns are going to be zeros. Okay, but of course that can only be done if you have a choice which basis you want. Yeah, if the basis is given, then you have to do the tedious computations. Okay, I hope that answers that question. Any other questions on 2.9?
No.
No. Okay. So then I'd say let's do 2.10. So, sorry, in 2.10, we have two matrices, A and B, and the task is to compute their eigenvalues and the algebraic and geometric multiplicities of these eigenvalues. So the matrices that we are considering are these. A is 2, 1, 0, 0, 2, 0, 0, 0, 1. And B is 1, 0, 0, 0, 2, 2, and 0, 0, 2. Okay, now if we want the eigenvalues, that's the first task that we are going to tackle. First thing we have to do is compute the characteristic polynomials. So for PA, we need to compute the determinant of A minus lambda E3. That is the determinant of, well, this matrix A here. Let me write that down again. And then we subtract lambda on the diagonal, like this. We want the determinant of this. As you can hopefully see, this is an upper triangular matrix, right? So there's only zeros here below the diagonal. And you know that for matrices of this kind, the determinant can easily be computed by just taking the product of the entries in the diagonal. So this is 2 minus lambda times 2 minus lambda times 1 minus lambda, or 2 minus lambda squared times 1 minus lambda. Okay, that means the eigenvalues of A are the roots of this characteristic polynomial. So we get 2 and 1. And the algebraic multiplicities are 2 for the eigenvalue 2 and 1 for the eigenvalue 1. It's basically this number here. Yeah, so this is the algebraic multiplicity, and here's 1. Okay, so once again, for A has eigenvalues 2 with algebraic multiplicity 2 and 1 with algebraic multiplicity 1. Okay, let's do the same thing for B. Again, we need to compute the characteristic polynomial. Let me write down B again. So that is the determinant of B minus lambda E3. So determinant of, so B was the matrix 1, 0, 0, 0, 2, 0, and 0, 0, 2. Then we'll subtract lambda on the diagonal. And again, this is an upper triangular matrix. So again, the determinant of that matrix is simply the product of the entries on the diagonal. So we get 1 minus lambda, 2 minus lambda, and 2 minus lambda. So we have 2 minus lambda squared, 1 minus lambda. And as you can see, the result is the same as for the matrix A. So B has the same eigenvalues with the same algebraic multiplicities. So that means B has eigenvalues 2, again with algebraic multiplicity 2, and 1 with algebraic multiplicity 1. So just write that down as well. That's the same as A. Okay, so even though the matrices are different, they may have or can have the same eigenvalues with the same algebraic multiplicities. Okay, how about geometric multiplicities? So that is going to be step 2. The geometric multiplicity is the dimension of the eigenspace associated with an eigenvalue. So what we have to do is we have to compute a basis for that eigenspace. Okay, let's see about that. We'll start with the matrix A. And we'll start with the eigenvalue 2. So the eigenspace associated to this eigenvalue 2 is equal to the kernel of A minus eigenvalue times E3. So that is the kernel of the matrix where A, let me write down A again, 2, 0, 0, 1, 2, 0, and 0, 0, 1. And then we subtract this eigenvalue on the diagonal. So minus 2 here, minus 2 here, minus 2 here. So what we get is the kernel of 0, 0, 0, 1, 0, 0, and 0, 0, minus 1. Okay. In this case, the problem statement does not explicitly ask for the determination of the eigenvectors or for the transformation matrix or for the diagonal matrix. We only need the multiplicity here, so we would be content with just knowing the dimension of that eigenspace. And that dimension is pretty obvious. We can rearrange that a little to see that even better. So we just swap these last 2 rows here. Well, we get a matrix that has 2 pivot elements. So that means the rank of that matrix is 2. It has 3 columns. 3 minus 2 is 1. So the dimension of the kernel will be 1. Yeah, dimension of the eigenspace associated to that eigenvalue 2 will be 1. And even though it's not necessary, let's determine the basis as well. So that eigenspace is spanned. For example, if you look at the first 2 rows, this row here, that gives you the equation x2 equals 0. This row here gives you the equation minus x3 equals 0. And by this column here, we know that x1 is a free variable. So x2 and x3 have to be 0. x1 is free. So this is a basis of the eigenspace. Yeah, 1, 0, 0 is an eigenvector. And of course, every multiple of that, every non-zero multiple of that is an eigenvector as well. Okay, so that's what we can do here. Then let's have a look at eigenvalue 1 as well, just for the sake of completeness. 1 has algebraic multiplicity 1, So we already know there is at least one eigenvector and at most one eigenvector. Yeah, there's always at least one eigenvector for every eigenvalue. And at most as many as the algebraic multiplicity says, at most that many linearly independent eigenvectors. So in this case, the dimension of the eigenspace is clearly 1. It can't be lower and it can't be higher. So the dimension of that eigenspace is 1. Okay, I'll compute that in a minute, but with respect to the problem statement, that would be all we needed to know. So let me summarize that first. So that means the geometric multiplicity of 1 is 1 for the matrix A. And as a summary, for the eigenvalue 2, we already computed that. The dimension of that eigenspace is also 1. So that is the geometric multiplicity of eigenvalue 2 for the matrix A. So that also means we do not get 3 linearly independent eigenvectors, and we are in R3. So we would need that many to get a transformation matrix, a basis consisting of eigenvectors. We cannot have that, obviously. So A cannot be transformed into a diagonal matrix. Okay, so there is no basis of R3 that consists of eigenvectors of A. And that means A cannot be diagonalized. Okay, and just for the sake of completeness, let me actually compute that eigenspace of A. Again, we don't need that for this problem statement, but just in case that you wanted to know that, or maybe you need it for some other problem statement. So let's quickly see that. Again, that eigenspace is the kernel of A minus 1 times E3. So that's the kernel of, we take A and we subtract 1 on the diagonal. So that is 1, 0, 0, 1, 1, 0, and 0, 0, 0. Oops, sorry. Like this. And that means, we're done already here. The second row, that would tell us x2 equals 0. The first row tells us x1 equals minus x2, so that's also 0. And we have no pivot element in the third column. So x3 is free. And that means that kernel is spanned by the vector 0, 0, 1. So that's the basis for this eigenspace here. And again, we have 2 linearly independent eigenvectors, so we don't have an eigenvector basis of R3 here. Okay, let's have a look at B next before we'll discuss questions about that. Should now be pretty straightforward here. Again, B eigenvalue, let's do eigenvalue 1 first here. Same thing as in A. Eigenvalue 1 has algebraic multiplicity 1, so it needs to have geometric multiplicity 1. So the geometric multiplicity of eigenvalue 1 is 1 for the matrix B, for the same reasons as with A. I'll leave the computation as a little exercise to you. So the interesting question is, what about eigenvalue 2? For eigenvalue 2, again, there is at least one eigenvector. The algebraic multiplicity is 2 there, so there could be up to 2 linearly independent eigenvectors. If there are 2, then we have this eigenvector for 1 plus those 2 for 2. and that means we have a basis consisting of eigenvectors. So let's have a look at that. Eigenvalue 2. So the eigenspace of B for eigenvalue 2, that is the kernel of B minus 2e3. So we get the kernel of, let's see, 1 minus 1 is, minus 2 is minus 1, 0, 0. Then for the second column, we get 0, 2 minus 2 is 0, 0. And for the third, we get 0, 0, and 2 minus 2, that's again 0. So we need the kernel of this matrix. And that's straightforward to see. The first row tells us x1 is 0. The other two rows don't tell us a lot, 0 rows. So we have two free variables, x2 and x3 here. And that means the dimension of that eigenspace is indeed 2. And if you want, you can determine a basis here. Let's use the free variable x2 first, sorry. x1 is always 0. And we'll just set x3 to 0 in that first vector. And in the second vector, we'll set x2 to 0, x3 to 1. Again, x1 is 0. So these are two linearly independent vectors that solve this equation system and that are then contained in the kernel. Okay, so that means this is the basis of the eigenspace. And the dimension of this eigenspace is therefore 2. Okay, so that means the geometric multiplicity is 2 of eigenvalue 2 is 2 for B. So all in all, we do get 3 linearly independent eigenvectors for B. That means there is a basis consisting of eigenvectors of B. Okay. There is a basis of R3 that consists of eigenvectors of B. And of course, that means B is diagonalizable. And of course, that is something that we could have known beforehand, because if you take a good hard look at B, then you will find that this matrix is actually in diagonal form. So of course, it can be transformed to diagonal form. Yeah, that would have been easy to see. But just in case it's not in diagonal form, this idea, this procedure will also work and tell you whether there is a transformation that will bring it into diagonal form. Okay, that concludes 210. Again, let's see what questions there are.
Okay, there was one question that I answered, but maybe you can talk about it. If I have a 3 by 3 matrix, but I only have 2 eigenvalues with both geometric and algebraic multiplicity equals to 1, what happens then?
Okay, so the question is, you have a 3 by 3 matrix. We have 2 eigenvalues with algebraic multiplicity 1 each. Okay, then basically what that means is your characteristic polynomial has only 2 roots, each with multiplicity 1. And as you know, at least if you're using the complex numbers as a basis, this cannot happen, right? Because every polynomial equation can be solved over complex numbers. So we have a 3 by 3 matrix. That means our characteristic polynomial will have degree 3. So the degree of the characteristic polynomial is 3. And that means we'll have 3 roots. Either 3 different roots, or the multiplicities need to add up to 3. So if we have 2 eigenvalues, 2 different roots, each with multiplicity 1, then we only have 2. Yeah, 1 plus 1 is 2. One is missing. Of course, it could happen over the real numbers, but specifically that is why we introduced the complex numbers, to avoid this kind of complication here. Yeah. So if you're working over C, and in these cases we will always work over C, then this is a scenario that cannot happen. One of these eigenvalues needs to have algebraic multiplicity 2. And then everything depends on the geometric multiplicity. So we're basically in the same setting we just saw. Okay, I hope that answers the question. Again, if not, please post a follow-up to the chat.
Okay, the second question here is, do I only need the algebraic and geometric multiplicity to say how many eigenvectors I have in the eigenspace?
Okay, so to know how many vectors you have in the eigenspaces, or the better question would be what the dimension of the eigenspaces is. Basically, you do only need the geometric multiplicities, because by definition, the geometric multiplicity is the dimension of the eigenspaces. Yeah, so you know the dimension if you have this multiplicity. Again, I'm not sure if that answers the question, actually. If it doesn't, please just post again.
I think it's good, he said. Okay, thanks. Yeah, the next question is, given the algebraic multiplicity is 1, the geometric multiplicity is also 1. Could you check this, confirm this?
Again, I'm not quite sure if I understood the question correctly. We've talked about this basically. So if you have an eigenvalue with algebraic multiplicity 1, then that means there needs to be at least one eigenvector by definition of an eigenvalue. Then there needs to be a vector with this property here if lambda is an eigenvalue. Yeah. So if lambda is an eigenvalue, then that means by definition there is an eigenvector or a vector v, so I'm sorry, with this property, and v cannot be 0. So the dimension of the corresponding eigenspace is at least 1, because there's at least this v that you can use as one basis vector. The dimension can be higher. It can be as high as the algebraic multiplicity. So if the algebraic multiplicity is 1, then we know the upper bound for the dimension is 1. Yeah, so we can say we have this eigenvector v already, that is one basis vector, and we know there cannot be any more linearly independent basis vectors because of the algebraic multiplicity. So we're done with that eigenspace. That was the argument that we used for the eigenvalue 1 for A and B before. Okay, any more questions?
Yes. Can one please explain the difference between algebraic and geometric multiplicity? I think you already told this, but...
Okay, let's write that down once more. So the algebraic multiplicity, let's start over here. Let's say we have an eigenvalue, a matrix, matrix A. We have an eigenvalue lambda. Then that means in the characteristic polynomial of A, well, lambda is a bad choice. Let's call that guy mu. So that means in the characteristic polynomial of that matrix A, that mu is a 0, a root, right? So there must be a factor of the form lambda minus mu that becomes 0 if and only if lambda equals mu. This factor may appear only once or maybe multiple times, so there may be some exponent k here, right? And then there are other factors, lambda minus, let's write this differently. So there are other factors as well. Lambda minus, how do we call this? Mu bar 1, and so on, lambda minus mu bar L, yeah? And maybe also with exponents, I don't care about those now. Then this here is the algebraic multiplicity of the eigenvalue mu. So basically the multiplicity of the root in the characteristic polynomial. Okay? So the algebraic multiplicity is the multiplicity of the root in the characteristic polynomial. And that's an upper bound for the number of linearly independent eigenvectors that could correspond to this eigenvalue, as we've just mentioned. Then if this is an eigenvalue, of course, we can compute an eigenspace. So this eigenspace, that would be the kernel of A minus mu En. And the question is, what dimension does this kernel have? How many linearly independent vectors are there in this eigenspace? And this dimension, that is called the geometric multiplicity of the eigenvalue. Okay? So we're interested in the dimension of this. So that is the geometric multiplicity. To repeat again, the geometric multiplicity is the dimension of the eigenspace for an eigenvalue. And as we've learned, a matrix can be transformed into diagonal form if and only if these multiplicities agree for every eigenvalue. So if and only if algebraic and geometric multiplicity are the same for all eigenvalues of that matrix. Okay, I hope that answers this question. Well, what else is there?
The next one is, could you explain again how one comes up with the specific values in the span from 2.10?
In the span from 2.10, anything specifically, or could I just pick anything?
Yeah, how one comes up with the specific values. So
I just start at the beginning then. Okay, so let's see about this. A eigenvalue 2. We've computed this matrix here, so we want the kernel of this one. That means we want the solution of the linear equation system, this matrix times x equals 0. Let me just copy this here. So I have a little more space to talk about that. Okay, so what we want is, we want the solution of the equation system, this matrix times x equals the 0 vector. That's, by definition, that is the kernel of that matrix, okay? And we do this basically by looking at the pivot elements of that matrix. We can see here that it has 2 pivots, here and here. And there's no pivot in the first column. And that means the variable corresponding to that column is a free variable. So x1 is a free variable. Yeah, because every column corresponds to a variable, x1, x2, x3. X1 is free. On the other hand, we can solve for x2 and x3 using the rows with the pivot elements here. So this row will help us solve for x2, sorry. This row will help us solve for x3. And if we do this, what we get from the first row is the equation x2 equals 0. What we get from the second row is the equation minus x3 equals 0. So same thing as plus x3 equals 0, right? And that means, what solutions do we get? Well, so this kernel here has the form x2 and x3 are always 0. x1 is a free variable. So every possible value of x1 yields a solution here. So this would be the solution space or the kernel. Or we can abbreviate that a little by saying, well, that's basically x1 times the vector 1, 0, 0. And again, every possible choice of x1 yields a solution. Or we could say that is all linear combinations of this vector 1, 0, 0, all multiples of that vector. And an abbreviation for all linear combinations of a set of vectors is to write the span. So this would be the solution for this first eigenspace here. Now let's have a look at the two-dimensional one as well. Yeah. Have a look at this one as well here. So the other one-dimensional one works just the same. And in this case, again, we want to solve this equation system here. When the kernel of the matrix is the solution of this equation system. In this case, there's only one pivot element, this one here, and two columns without any pivots. Columns correspond to the variables x1, x2, x3. So that means x2 and x3 are the free variables here. Okay, so the solution space in this case, well, the first row here, that corresponds to the equation minus x1 equals 0. So x1 is always 0 in every solution. And x2, x3 are free. So every choice of x2 and x3 yields a solution. That means all solutions will be of the form 0 and then x2 and then x3, where x2 and x3 are arbitrary real numbers, or even complex numbers if you're doing complex numbers here. Okay, so we can also write this in the form x2 times 0, 1, 0 plus x3 times 0, 0, 1. Yeah, just an expanded version of the vector that we had before. And again, what we see here is a linear combination of the two vectors 0, 1, 0 and 0, 0, 1. Any linear combination will do because x2 and x3 are arbitrary. So this is the set of all linear combinations of these two vectors, or just 0, 1, 0, 0, 0, 1, and then the span over these two. And that's how I came up with the second solution. I hope that explains it sufficiently. Any more questions? Tiago?
Hello? Hello? Do you hear me?
Yeah, now I'm hearing you.
Okay. Yes, there was one more question, but not related to this, but to complex numbers. Should I ask this? Or?
Did we talk about that question that we deferred in the beginning? Or has that been answered already?
No, this has not been answered yet.
Maybe we do that first and then refer to other questions.
Okay, wait. There is one more question here. Okay, about 2.9b. Can I ask this one now?
Anything about Eigen Vectors, Eigenvalues, yeah. And then we'll open up the stage for other questions.
Yeah, this is related to eigenvalues. So
great, yeah, let's ask that one first.
In 2.9b, why can we say that if we know that u and v are orthogonal, that the eigenvalue will be 0?
Why can we say that if we know that u, so that's basically, okay, we have this u, we have this v, and we know that u and v are orthogonal. And by definition, remember that means the scalar product is 0. Okay, and so, well, what is f of v? Again, we just use the definition of the projection. That's this scalar product here, divided by the norm of u squared times u. And this scalar product is 0. So the outcome is 0, 0 vector. Yeah, and of course the 0 vector can be written in the form 0 times v. So that means v with an eigenvalue of 0 adheres to this definition of eigenvalue, eigenvector. Yeah, definition was mapping applied to v is a multiple of v, and that's just what happens here. We get a multiple of v as the output, and the number that we multiply with is 0. So by definition, 0 is an eigenvalue and v is an eigenvector. That's basically because this scalar product here becomes 0. So that's true for every vector v that is orthogonal to u. Okay. Did you find that question about eigenvectors, eigenvalues from the beginning?
From the beginning, yes, but I already answered it and I guess it was fine.
Okay, good. So then let's see if there are any other questions, possibly about complex numbers as well.
But maybe you can answer again. He said, I think he didn't understand. So the question was, if my matrix is not diagonalizable, does it automatically means that it doesn't possess an eigenvector basis?
Yes, so if you have a matrix that cannot be diagonalized, that means there is no transformation that gets it into diagonal form, then there is no basis that consists of eigenvectors of that matrix. Because if there were such a basis, then this could be used to get a transformation matrix that brings the matrix into diagonal form. And if that's not possible, there cannot be such a basis.
Okay, he said thanks.
Okay, great. What else do we have?
Yeah, I guess this is the last one. So about complex numbers. So how can I use Euler's formula when I have a value like exponential to the power of 2 minus 3 times I, everything times t?
Everything times t. So like this here?
Yeah. Yeah.
Okay, so and I guess t is a real number, right? I hope so. Otherwise, things get more complicated. Okay, I'll answer for the case that t is a real number. Otherwise, you just bring it into that form somehow. Okay, so as you know, again, let me write down Euler's formula. That was this here: e to the ix equals cosine x plus I sine of x. So what is important about Euler's formula is that we have this I times real number. Yeah, x is a real number. In this case, we don't have that form because there is a real part here, right? So we have this imaginary part, this one here, and we have a real part, purely real part, okay? So we have to first apply a little algebra here. Let me first bring that t into that product here. So that is the same thing as 2t minus 3it, right? And then we just apply rules of working with exponentiation or exponential function. This is the same thing as e to the 2t times e to the minus, let me write that differently, to I minus 3t. Okay, so we use that sum, we split it up, and we turn it into a product using rules of exponentiation. And then we can again apply Euler's formula. We just take that 2e to t, we just take that e to the 2t, that is a real number, so no problems here. And when we apply Euler's formula to that second part here, and that is cosine of minus 3t plus I sine of minus 3t. Okay, so we need to make this split first, and then we can apply Euler's formula to the purely imaginary exponent. That should hopefully answer the question. Good. Any more questions?
Yeah, I said got it. So I think that was the last one.
Great. Okay, then thanks, Tiago, for moderating. Thank you all for attending the webinar. As always, the recording will be available on Moodle probably sometime tomorrow. And hopefully see you on Thursday or next Monday in the next central exercise session. So see you then.